what type of material you should select. So yeah, next slide please. Yeah, so for solar cell application, we generally use semiconducting materials. Uh, now, now, yeah, please stop. So now, so you generally use semiconducting materials for the solar cell application with a band gap less than 3 electron volt. Now, there are various types of semiconductor materials available which have the band gap in this range. Now, how to select a good solar cell absorber material so that it can absorb most of the solar radiation? Next question is that one. So, the middle diagram, solar radiation spectra. So this is the solar radiation which we are receiving on Earth from the sun. So it consists of like UV region, visible region, and the IR region, and you can see the maximum radiance you are receiving at around 500. So we generally need to have a semiconductor. Means we generally need to select semiconducting material in such a way so that it can absorb most of the solar radiation and will generate we generally generate electricity in terms of current and voltage, so actually power. So we need to select accordingly. What happens now? The next question is what happens if I select like randomly semiconducting of any band gap. So if your band gap is less than the photon energy, so photon energy is the energy of the photon which are you are receiving from sun. So if your energy is lower, means your band gap is lower than that. Okay, so band gap is lower. The second diagram. So your means that will knock out electron from the valence shell, and that will go to higher energy state in the conduction band, or else on the from the periphery of the valence band also it can excite electrons to the very high energy level in the conduction band, and after some time when means like they will relax and come down to the periphery. So in that case there is some loss of energy which is thermalization loss. So there will be heating of the devices, so your solar cell will get more heated and there will be more losses in your solar cell. Another problem is like if your band gap of the semiconducting material is high than the photon energy, then in that case your radiation will not be absorbed and will directly penetrate through your material. So you need to select material in such a way that it can absorb most of the solar radiation, as well as there will be no thermalization or very less thermalization losses. Next, please. Yeah, so how a solar cell works. So these middle layers you have seen in the previous diagram or previous slide also. So firstly, your solar radiation is absorbed by the semiconducting material and your electron will be excited to the higher energy state, leaving behind a hole or a vacancy in the valence band. This you all might have studied. So what happens is then this electron, which is in the high energy state, can come back to again the valence band after some time. So, but for solar cell application, we need to separate these charge carriers. We don't want them to recombine, because if they will recombine, then it will not be a solar cell. It will be like a LED. So we have to stop this recombination. We have to separate them. For that purpose, we apply extra layers along with that, so that that are called electron transporting layer and the hole transporting layer. So electron transporting layer are selected in such a way that the conduction band of those is lower than the conduction band of your absorber material, so that your electron can easily means move towards that side. Similarly, your hole should be able to move to the whole transporting layer with the valence band bit higher than your valence band of this semiconducting material. And further, after it reaches to another layer, means after separation, our work is to like collect these charge carriers so that further we can use them at the time of the need, and then we can store in some cells also. Now, how to identify that a cell, our solar cell, is working properly or not? So there are few important parameters for any solar cell. JSC, yes, next, VOC, fill factor, and efficiency. So JSC is short circuit current. This is short circuit current density. In solar cell, we generally talk about current density in spite of the current, because we have various type of the solar cells, and if we have to compare them, then we need to compare them on the basis of particular area, how much current they are generating, so, or the power they are generating. So we generally talk about current density or power density in solar cells. So this is short circuit current density. It means when external load, if there is no external load, the connection is short circuited. So then there is short circuit current density. In that case, there will not be any voltage in between. So the voltage is zero. On the other hand, VOC is the open circuit voltage. It is actually when your load is open circuited, means out after means your solar cell, the connections are open, so in that case there is no current. Then there is VOC effect, and then the fill factor is actually measured as the squareness of your uh, IV characteristics or the JB characteristics. So, and efficiency depends upon actually all the factors. Next. So this is the NREL chart. In this, they have, so you can see on the top, multi-junction cells, single junction, gallium arsenide, crystalline silicon, solar cell, thin film technologies, emerging PV technologies. So we have various types of solar cells. Today's our topic is on perovskite solar cell, which is a type of emerging PV technology. Along with that, there are some other technologies like thin film, and silicon is itself a dominant solar cell technology. So if you see this dark square or this empty square, you see their IV characteristic. It starting means around 1985 or something, and up to 2020, the efficiency is around 23.3 and 26.1%. Whereas if we talk about perovskite solar cells, they started recently, and they have reached the efficiency of around 25.2%. So this is the beauty of perovskite solar cell. These are emerging PV technology, basically thin film PV technology, which are showing so much enhancement, the promising results in the photo conversion efficiency. So that's why and also the less material is required, no much processing cost is there, and can be easily made in the lab. So that's why the focus is shifting towards perovskite solar cells. Yeah, stability is one of the issue with these as compared to our dominant silicon technology, but in rest of the cases this is performing better actually. Next slide please. So in perovskite solar cell, means perovskite itself is not a new field. In 1839, CaTO3 perovskite was discovered, and then its crystal structure was determined in 1958 for the cesium lead halide based. So in this, perovskite is actually perovskite actually have ABX3 crystal structure. So you can see the diagram in 1958 one, where B and X together make this halide structure, and the A is generally the cation in between. Then in 1978, this was replaced with Ma positive, the methyl ammonium cations, and then that one was the first one which was used for the perovskite solar cell application. Means it was discovered in 1978 and first came into picture in 2009. So it took a lot of time to reach to solar cell application. Then in 2009 it was DSSC type. So then 2012 solid state perovskite solar cell devices were made using the spirometred whole transporting layer, and the efficiency was reached from 3.8% to 12%. Then later, from 2013 to 2015, lots of work was done in this field in terms of the material selection, the perovskite film quality improvement to reduce the resistive effects in the solar cell, and also the addressing the hysteresis effect and interfacial engineering with the electron transporting and the hole transporting layers. And then later in 2016 to 17, the research was done in the field of material selection, and then high quality perovskite film formation and the interfacial engine. Then 2017 to present, now people are working on scaling up this. There are lots of startups in this field now, and also on the inorganic lead halide perovskite to improve the stability of these solar cells. Next, please. Yeah, so fabrication procedure of perovskite solar cell. Fabrication procedure is very simple. So in this, you take FTO substrate, okay, and on that you coat your electron transporting layer, and after that you make a perovskite solution using the lead halide and MAI in DM over DMSO, and then you just spin coat it and anneal it. Your absorber layer is ready, which will absorb your solar radiation. Another method is like in the first method, sometimes there is roughness issue. To solve that, people are using anti-solvent technique. With this, you get a very uniform and shiny film. So if you want to see that your like some of you might be working in the solar cell field, so after depositing your perovskite layer, if you want to check your device is going to work good, means work nicely in the future, for that purpose you just can check the how shiny it is from the back side, from the FPO side. If you see it's shiny, it means the interface is good and your device is going to work good. Another method of perovskite deposition is the two-step method. In this, firstly you coat lead halide film. After that, you coat MAI in any of the ways you can you want, like either in IPA solution, dipping in that, or else you can spin coat it. And another method is just heat it in MAI vapors. Methyl ammonium gas also you can use, and then further you can use anti-solvent or something for spin coating for the shiny interface, shiny film and the better interface. So this is the MA is methyl ammonium iodide. So these two and these are the normal conventional perovskite solar cell. You can see this oily yellow part is the gold one, and on another side you can see the gold is behind. So this is, your light enters through the FTO region, and the gold is your back electrode, your front electrode is your FTO. Now, how it works is in this Venn diagram. So, when your sunlight falls, then it excites your electron to the higher energy level, and then that electron will go to your ETL because of the conduction band is near to the conduction band of your perovskite. Similarly, your hole will go to the hole transporting layer because we are separating charge carriers. So, we introduced hole transporting layer with the valence band near to your valence band for perovskite layer, and then this will go to your electrode. Similarly, your electron will go to your FTO site, and then these will be collected. Next, please. So now classification of perovskite solar cell on the basis of electrode type. So these are actually metallic electrode type and the carbon-based perovskite solar cell. So metallic counter electrode based is in which we are using gold, silver, all these electrodes. So in these, the advantage of these is high efficiency, also like solution processable, easy, and all this. But you generally need to do all the processing in the glove box. So and very specific instrumentation is required for and in
Kindly
this
mute yourself. Hello,
and also
all participants, kindly mute yourself.
And also in this, you make use of whole transporting layer like spirometed and all. These are all equivalent, means their cost is equivalent to the gold, so are very costly materials and unstable also. And the metal electrodes we generally deposit by thermal evaporation, so that is also like sophisticated instrumentation and loads of electricity is required, and the lower stability of these solar cell are very sensitive to moisture. Whereas carbon-based perovskite solar cells, these have lower efficiency than the metallic counter electrode based, but these you can easily make in ambient atmosphere, no need of any glove box, and you just screen print these and your solar cells are ready, and they have better stability because of the carbon layer or the on the top, which is hydrophobic, so which don't allow the moisture to penetrate deeper inside your solar cell, and you can use this solar cell in the external atmosphere. Yeah, Rishabh, please. Rishabh, uh, yeah, these are some of the published articles in the field of the perovskite solar cell. So you can see number of publications are very high in normal perovskite solar cell, while carbon-based perovskite solar cells yeah, very less. And these are the two types of carbon-based perovskite solar cells: high temperature-based and low temperature-based. What is high temperature-based is in this almost all the layers are almost all the layers are screen printed and are annealed at a high temperature around 400 to 500 degrees Celsius. And the low temperature based are actually type of planar kind of structures. So in this, each we generally use spin coating technique, and the later carbon electrode is deposited using blade coating or the screen printing technique. So you can use any of these. Yeah, next please. So challenges with the carbon-based perovskite solar cells are a lot, because their efficiency is lower than the conventional gold-based devices, but with few advantages. So lower efficiency, VOC is less, and the fill factor is also low. His stress is low, and the response is low because the mesoporous structure is very thick in this case. Like carbon layer is 10 micrometer thick, and your insulating scaffolds are around 1 micrometer thick. So this is a very thick structure, so that's why response time is very slow in this case. Yeah, next. So there are various aspects by which we can improve the photoconversion efficiency of these solar cells, like either by perovskite engineering, we can play with the perovskite so that we can improve the VOC, because your conduction band and the valence band of the perovskite matters a lot for the VOC. Similarly, your carbon electrode engineering, because your carbon electrode work function is less than your gold, and also in carbon-based perovskite solar cell, there is no hole transporting layer, so the gap is huge from valence band to directly your electrode. So in that case, losses are more, and your VOC is affected because of the quasi Fermi level. Another is the electron transporting material engineering. Like we are using conventional TiO2 base, so we can improve that also for improving the stability, and interface engineering between the various layers. Yeah, next please. Yeah. So before moving to this part, I would like to tell everyone that I am working on this carbon-based perovskite solar cell, especially on electron transporting, Hall transporting, and the carbon electrode part. Perovskite is not my part, so I'm working on the screen printing paste preparation for these carbon-based perovskite solar cells. So how we generally prepare screen printing paste is just ball mill all your material with organic binders and solvents, and then you then rota evaporate and your paste is ready, and then screen printed. So yeah, next please. Yeah, so there are various reports on improving the performance of the carbon-based perovskite solar cell. My work I haven't published yet, so that's in process. So I can't share that data. So I'm uh, sharing all the literature which I read for improving the device properties. So, firstly, I have worked on carbon paste. So, in that, there are few reports on the carbon electrode engineering in the literature. In the first report on carbon-based perovskite solar cell was in 2013 by QATL. In that, they checked the different types of graphite, like two types of graphite, the flaky and the spheroidal shape graphite. They check the effect of the shape on the performance of the carbon-based solar cells, because in carbon-based solar cell we infiltrate from the top of the carbon layer after screen printing all the layers. So they checked how the morphology of your graphite is going to affect your carbon-based solar cells property. So they found that if you are using spherical, then you have the more surface area. So in that case, they found the spheroidal having the higher photoconversion efficiency as compared to your flaky carbon-based solar cells. Similarly, in 2050, Jung et al. They checked the effect of the flake size of the graphite on the performance, and they came up with the 11.63% efficiency from the first. This was the second one. So 11.63% efficiency with the 9 micrometer size of graphite. So if anybody of you is planning to work on the carbon-based perovskite solar cells, so these are some of the points which you can pick to improve your devices. And another study was on the thickness optimization. So in this, they check the effect of the thickness, and the thickness of carbon layer is generally in the micrometer, because if it's thin and you anneal it at high temperature, so they generally came out in the form of the like, because they are carbon. So if you anneal to high temperature, they just come out of your, and there is a delamination issue. Next is another study in which they use the aloe vera to check its effect in the carbon paste, and like how there is cross linking and how much porosity will be there. So they found that the cross linking is better, and as well as the porosity is improved. So they found around 12% efficiency in this case. Next issue. So further study was on the VOC improvement of the carbon-based solar cells. The VOC is one of the major issue in the carbon-based solar cells, because your gold-based devices generally give VOC around one electron, more than one electron volt, and achieving that much VOC is generally a very big target in carbon-based solar cells. So there are few studies in which they done studies on perovskite engineering, hole transporting layer introduction in between, so that your Fermi level, so that your valence band of will be near, and your hole will not directly go to your carbon electrode. In that case, the VOC can be improved. Next is carbon electrode work function directly by adding some dopants in that, and the interface improvement. So this is one of the study in which before perovskite infiltration, like they kept means they done some oxygen treatment on their carbon electrode, and they found that there is shift in the work function, which automatically uh, leads to improvement in their VOC. So as I already discussed, like in the more closer your valence band of whole transporting layer to your perovskite, then in that case less will be the losses, and your VOC will be improved, because your quasi formula will split. So all these factors will be affected by that. Next is in this report also they added nickel oxide. So they modified the work function of the carbon electrode. This is the pure carbon electrode having the work function around 4.94, and then 10% nickel oxide it shifted, then 30% nickel oxide it's for more than around 4.99, and then for 50% nickel oxide it reached to 5.04. So they checked the effect of this modification on the device performance, and they found that if you shift the work function of your carbon electrode more near to the valence band of your perovskite, in that case the VOC will directly improve. And the similar effect they have seen with this impedance analysis, like your series resistance is less in that case, so they are reduced, means the resistive effect is reducing, as well as your transport resistance is also reducing in case of by addition of nickel oxide, and by lowering means your the work function of your carbon electrode. Similarly, there is one more study in this. They check the effect of boron addition, like to nickel oxide. It's also the P-type material, and in this also they found the improvement in the VOC with the addition of. Next time, Rishabh. Yeah. So another study on the VOC improvement is by improving the interface between the TiO2 and the perovskite layer. So in this case, they added a ferroelectric layer by solution by means dipping uh, in the solution of PbI-3, and then they deposited perovskite layer, and later they just CNT they spray coated on that. So this is one of the techniques. This is low temperature based electrode. So in this case also they found that by adding one extra layer, so you know that the difference between PN and PIN is like in PIN the depletion width increases. So they check the effect of that on the increasing the depletion region width and increasing the built-in potential of your layer means of your solar cell on the device performance. And they found that if you increase the depletion region width, so with that your VOC will directly improve. Similarly, your JSC and almost all the factors are improving because like 75% fill factor they have achieved with this. So this much fill factor is also very hard to achieve in the carbon-based solar cells. And these all things they have shown with the these are the device performance analysis and the IPC, the how much reason they are absorbing. Then the PL intensity is showing that the more quenching with the addition of this layer, indicating that the faster charge separation in that case. And this there is carrier lifetime increases, and the impedance analysis also revealing that as your PBR23 is adding into that, so at lower frequency, uh, your the impedance is increasing in this case, so which is showing the improvement in device performance directly. Yeah, so that is also with the we applied to the recombination. And another study is with the addition of this nickel oxide, and they use the mixed perovskite in this case. So generally, what we use is MAPBI3 as a perovskite in the carbon-based solar cells. So in this, they tried with the mixed cation perovskite in so triple cation they used, and they found that because I was already discussed the band gap of your perovskite is going to affect your VOC directly. So they found that thing here also with the addition of cesium in that, because cesium will increase the band gap. So in that case, VOC is higher than 1. So, and your fill factor is also 72, and 17% efficiency there is achieved in the carbon-based solar cell. So, yeah, next, Rishabh, next. Yeah. Now to improve the photo conversion efficiency also, and to for the one more problem with the carbon-based solar cell is that when you check the device performance, you need to soak light for a longer time in that case, because yeah, the thickness of the structure is very high, and also your perovskite thickness is also very high. So it takes time for getting better efficiency in that case. So to improve that effect, like to for faster response, and we don't need to soak our device, we don't need to do light soaking for longer time. There is one report in this they used humidity treatment. So in this, after device fabrication and perovskite infiltration, they kept the device in the moisture and atmosphere for some time, around 200 hours, and they checked the effect of that on the device performance on 115 hours, and they just checked the effect. And they found that if your fresh device is giving efficiency around, if I'll take on average 9.2%, and after your HT treatment, the efficiency reached to 13.8%. It means, and also you see the resistance of the cell is reduced by, because moisture will try to link, because moisture will not penetrate through your carbon layer to your perovskite layer. It will be on the top, so it's going to it will improve the connection between your graphite layers and the carbon of the carbon electrode. As a result, the flow of the charges will be better, and your device performance will improve, and resistance will reduce. So they checked the effect of this, and they found there is improvement in device performance. Because if you see the companies or some startups are coming forward in the perovskite solar cell, but very less are for the carbon based solar cells, because they need to soak they need to do light soaking for longer time. So to overcome that problem, this can be one of the practical solution can be utilized there. Another problem in the commercialization of the perovskite solar cell, and also in the lab based solar cells also, is infiltration. Like when you make smaller devices, it's you just infiltrate with your pipette and it's very easy. But when you go to the larger scale, you make modules or something. So in that case, when you infiltrate drop by drop, the drop will go and will like spread it all over, and and at the last there is some region is still remaining, and we by our naked eyes we don't come to know that. We think our device is completely infiltrated, but the region still remaining there. So there is one more approach came forward, is using the slow dye coating. So slow dye coating we generally used for normal perovskite solar cell. In this they use that for the carbon based solar cells, and they check the effect of the speed of this, and they found the moderate speed, the flow rate control they mentioned in the paper about improving the device performance in the slow time. Yes, Rishabh, next slide. Another approach, as I already mentioned, that your whole transporting layer or either the work function or your carbon electrode matters a lot. So you can see the band diagram here. If your valence band is here and the carbon is around 5.0 or 5.1 after some modification. So if there is a gap increases, the VOC loss will increase. So yeah, in these cases they added one more whole transporting layer. There are some more reports on that. So I covered all these two only. Like these are not yeah. So one generally people uses nickel oxide layer there, but in this they use the copper dope nickel oxide layer, and in this the efficiency improvement is better as compared to normal nickel oxide. So I covered this paper here, and the VOC is, so in this case, the VOC is around one. Achieved with this case, and with a photo conversion efficiency of 12.65%, with a aperture of zero point 0.8 centimeters square. And another one is using the CO3O4 spinal. These are the spinal materials. So in this case also, it's all about your band engineering, like which type of material you are going to select. It should be porous for the carbon based solar cell and should have the band alignment almost near to your absorber layer for better performance of your any type of solar. So these are the things you need to remember, and in both the cases, you see the similar results, like improvement in the device and the better PL quenching as well as the large carrier lifetime. So that is the common story for all the solar cells. Just you need to, whenever you are selecting some material, you need to select in such a way that the conduction band should be near to your conduction band of your absorber, and this similarly valence band also. Later on, it doesn't matter. Next, Rishabh. So this is yeah, a bit funny also. So if you have a perovskite solar cell, like some of you might be working on, and you add carbon electrode in that case, then what will happen? Your cost will reduce. You are not using gold. You are not using costlier whole transporting layer. Similarly, you are doing all like in the ambient atmosphere, so cost is definitely reducing. Similarly, CO2 production is not there, which is generally in case of the silicon-based solar cells, and no pollution, and all the materials you can synthesize by your own in the lab. And as the cost is reducing, so this thing can be like this application. This can come into picture in the commercialization and can reach to every place, to every household who need this. And similarly, we can make flexible also using slow dye coating and the low temperature carbon electrodes. So what we need for the carbon-based solar cell is screen printer and your screen printing paste. That's it. No glove box. Yeah. Yeah. Next, Rishabh. Thank you. Sorry for delay.
Thank you, Priyanka, for a very great talk.
Yeah. Thank you.
Yeah. So now the session is open for questions.
Okay.
I think my voice is getting good. I request everyone to mute yourselves. Yeah, please. So now we'll see, Priyanka, we can take questions from the chat box first. Yeah, hello, Priyanka.
Yeah. I'm reading that. Yes.
Okay, so shall I read them or you read?
Uh,
Priyanka, I suggest Anupma will read the questions and you answer.
okay. That's also fine.
Okay.
Okay. So yeah, we are going to our first question from Pradeep Naik sir. So he wanted to know what is the range of fill factor for a good solar cell?
Actually, fill factor. May I speak?
Yeah, you can.
Yeah, fill factor like it tells the squareness of your curve. Like when you are checking your device in the dark, like what is your JC, VOC on the illumination on the ideal, and what is the maximum power you are getting. Similarly, you get Vmax and the Imax. So depending upon that, there is a gap between both the rectangles. So if this ratio of these rectangles increases, it means you are going far away from the better device. So you always try to achieve the means like the maximum area of that curve. I don't know how to explain this on this video. I don't have graph now.
Priyanka, do you want me to open the presentation?
No, it's not in presentation.
Okay.
Okay. So Priyanka, shall I go to the next question?
Yeah,
You want
please
to
next
start?
question. Yeah.
So next question is from Abhiram Anand. I want to know what is MEI?
Huh?
What is MEI? I think you might have used it somewhere in the
MEI,
presentation.
methyl ammonium iodide. Yeah.
Okay. Okay, so that's good. So next, we take up question from Preeti Thakur. So she wants to know, like, is there any uh, rules that while calculating lattice parameters from XRD, we need to consider the peaks of relatively high intensity?
Actually, I'm not working on perovskite part, so I won't be able to question on perovskite. Sorry.
Okay.
Yeah, I'm working on
Yeah, okay. So
perovskite.
next question again from Preeti. What is the maximum open circuit voltage we can get in perovskite solar cell for ideal condition?
So for ideal condition, it depends upon the band gap of your absorber layer. So, like,
Okay.
yeah. So whatsoever the band gap of your absorber will be your VOC. Maximum VOC you can assume, but there are always recombination and other losses, so we don't able to achieve to that value.
Okay. So again, a question from her only. What are the best materials for inorganic hole transport in perovskite solar cells?
Yeah, inorganic her transporting layer nickel oxide is good, along with that QCN and all. You can use.
Okay. So next question is from Girish sir. We want to know how can we use bismuth ferrites in solar cells?
Uh, Again, I'm not sure about this one.
Okay. So next question from Kishore. So he wants to know a general question about germanium band gap is smaller than silicon. Then what is the difficulty in this to be commercialized, like germanium in spite of silicon? So you want to know this.
Germanium.
Yeah.
The
Like I think his question might be like using silicon solar cells and not germanium. Maybe. Not
yeah,
sure.
I think it's toxic and like not that much abundantly available. So that's why we are switching towards material which we can easily synthesize and can use in solar cell application.
Okay. So Shri Devi ma'am is asking which equipment is used for screen printing?
Screen printer we are using, and that is from Nikko company. Like use camera of that company, so it's from same company.
Okay. So next question from Preeti. What is the longest lifetime reported for electron holes in perovskite solar cell today?
No, not sure. Sorry.
Okay. So next is from again Preeti Thakur. Sir, how like current density and voltage measurements taken using solar simulator for perovskite solar cells? So
How
how to
Jane
take JV measurements, current
using solar
density?
cell? Yeah, you just
Yeah.
connect. Yeah, you just connect the positive terminal of your electrode to the the positive terminal of your machine to the electrode, gold one, and the negative terminal to the FTO side, and then just measure, illuminate it from the FTO side.
Okay, so I hope it's clear. So next question again from Preeti. How to connect the crocodile flips to doctor-graded carbon paste perovskite solar cell to measure its efficiency?
So whenever you are using carbon-based solar cell, you can either use silver paint on the side for making contacts, because if you will put crocodile clip directly on the carbon layer, it will be peeled off. So either yeah, you can just put any
silver
paste. Yeah, silver paste is also fine.
Okay.
Or solder,
So next,
you can do soldering also.
yeah, soldering also you can.
Yes.
Next question is from Mahalakshmi, ma'am. So she wants to know how nickel oxide can be coated. What is the synthesis procedure?
Nickel oxide, you want to coat for which type of perovskite solar cell? Like there are various techniques. If you are using low temperature based techniques, so in that either you can use uh, sputtering technique, ALD deposition, as well as by solution dipping technique. And if you are talking about high temperature, then you can make nickel oxide paste and can just deposit that. There are various reports on that available.
Okay. So Dr. Ram is asking, you can prepare, like, how can you prepare paste using ball mill mechanism? Then how are you ensuring paste quality? I think it should be best quality, maybe. I don't know. So, Dr. Ram, can you unmute yourself and directly ask? Actually, I'm not sure if I'm saying the correct question.
Hello.
Hello.
Yes, sir.
Are you hear me?
Yes, yes.
Yeah. My question is that when you prepare the paste, how you ensure the paste quality and structural integrity? Because ball milling may affect the structural integrity.
Yes, ball milling affects, but like in our paste, we are monitoring the ball milling time. We optimize those things like ball milling time and the solvents you are using, even your ethanol and all these solvents you are using. How much amount you are adding, that will also affect your material property. So that depends from material to material. Like I'm making porous, so I'm adding some other materials in that. So after annealing, those will burn and they will create pores inside that paste, means that electrode, and then I use infiltration technique. It depends the type of polymers and all these things we are using, and the ball milling time.
Okay, because I am also using same
And even
quality slurry
yeah,
because
even your like number of balls you are using, the type of ball mill you are using, that will also affect your paste property, paste rheology.
But if we are using that, then if material is not single phase, then phase will be changed.
Phase properties. No, phase properties I haven't
Yeah,
studied. Yes, phase properties I haven't studied. So I'm just
because most of people are to change the particle into
yeah, that will depend. Like when you are ball milling, there will be some heating effect also.
water.
So like I don't know your material, so you need to tune the ball milling time, your speed, and also the type of solvents you are using. All these factors will affect that.
Okay, so I hope, sir, it's clear.
Hello.
Uh,
Yes.
Hey,
So we can go. Yeah, so we can go to the next
if there is
question.
still some doubt, then my email ID was there, so you can like can tell me directly the material. I can tell you about that.
Okay. So thank you, sir. So next question is from Vishal Sharma. So you want to know why you called binary oxide like nickel oxide and clear to us perovskite? Any specific reason?
What?
why you called binary oxide like nickel oxide and TiO2 as perovskite?
No.
Is there any specific reason?
No, I won't call them perovskite. I'm using them with the perovskite. Perovskite is my absorber. They're my electron transporting and hole transporting layers.
Okay. So I hope that is clear. If not, you can directly ask. If directly communicate. Yeah. So next, going to Aryan's question. What is the effect of heating on energy efficiency of heating? Yeah, sorry. What is the effect of heating on energy efficiency of perovskite PV cells? To what extent their efficiency is affected?
Yeah, it will be affected like in any of the solar cells. Like your VOC is directly related to the temperature. So if your temperature will increase, directly your VOC will be affected. And your efficiency is a combined effect of all your JC, VOC, and fill filter. So that will have a direct effect on that. So there is a mathematical relation for that. Yeah.
Okay. Okay. So next question is from Vera Ram sir. So PB is very toxic. So how can you change it? PB, lead.
Yeah, lead is toxic. So people are coming up with some other like metallic metallic materials like SN2 positive, which generally like changes its phase to SN4 positive. So now there is one more. So like research is going on, but they haven't came up with some other materials. These two are the most promising one till now. Lead is giving higher.
Next question is okay. You can continue.
Hello.
Yeah, Priyanka,
Yeah,
you were saying something.
people are
Yeah,
still people are still using lead because of higher efficiency, but research is going on that, and SN is one of the alternative. There are various reports with that also, but efficiency is lower than the lead based.
Okay, so it's under research. Yeah. So next question from Preeti. Role of DMF and DMSO in perovskite. Yeah, organic solvents, DMF and DMSO. Yeah.
Yeah, DMF and DMS actually are for dissolving your material, and if you if you are only using DMF in preparing your solution, then you will get very rough films. That's why people generally add little bit DMS in that, so as to improve the film quality.
Okay. Okay, fine. So next, can I use FTO quartz instead of FTO glass in perovskite solar cell? Preeti is asking.
Can use FTO.
Quartz. FTO quartz.
FTO quartz. Yeah,
Quartz.
if you are having FTO with the similar structure like that, yeah, it will be costly, but if you can if you can use it, it's fine.
Okay, so like FTO glass is fine or FTO quartz? Like what do you suggest?
No, for you, like the upper layer should be FTO, and there should be good your light should penetrate easily through that. There should not be reflection and all these phenomena. So you need to select accordingly.
Okay. So next question from Veera. Yeah. Can I use PDMS and replace DMS? I think it should be DMS. PDMS and replace DMS.
Where is the question?
It's at like from bottom you can see at 6:36 p.m.
Can I use PDMS and replace DMS?
Yeah.
No.
So
DMS, that's DMS too.
yeah, maybe it could be DMS. Maybe. Or you can directly
I can directly ask. Yes.
Veera Ramsa, kindly unmute yourself and directly.
Yeah, my email ID was there in the beginning, so you can ask me directly.
Okay, so take up later. Next, we can take from next question from Adrian. That ma'am, you told that perovskite PV cells will be affected. I want to know the effect of heating efficiency as compared to silicon PV cells.
Yeah, like in perovskite itself, there is organic, inorganic materials we are using. So generally, the structure will be affected a lot, while your silicon is inorganic, so that can bear that one with that loss. So that losses will be more in case of perovskite solar cell as compared to silicon,
Okay.
because it will degrade that. Yeah.
Okay. So next question from Vinod. What is the work function of perovskite?
Uh, is it minimum band gap?
Minimum work function. Yeah.
No, no, no. For perovskite, like we generally talk in terms of band gap, and
Band gap.
band gap can be tuned to 2.3 electron volt.
Okay. So next question, last question for the evening from Preeti. So how ferroelectricity may affect the photovoltaic performance of perovskite solar cell?
So, I discussed in one of the use the ferroelectric material there. So after depositing that layer, we need to polarize that in a particular direction so that there will be permanent dipole moment, and then that will act as one of the will promote your depletion region, and width will increase, and definitely your performance will improve because your built-in potential will increase.
Okay. Yeah. So any other question anyone would like to ask? You can unmute yourself and directly ask Priyanka.
I'm writing my email
More
ID
questions?
here in the comment section of
Chat box?
yeah, chat box.
Yeah.
Then can directly contact me.
Okay. So I think yeah, thank you, Priyanka, for the talk.
Yeah, thanks Anupma for such type of sessions. Yeah, it's really helpful.
Yeah, thank you so much for your time.
Yeah.
So I think before starting this session, Abhishek sir, your introduction was pending. Like you were saying something. So I request you to unmute yourself and continue with your.
Hello. Before we start with the interactive session, I would like if we can take up the photograph, and if there are any queries left for Priyanka, we can take that too. And after that, we will go with the interaction session.
Okay. So you want group photograph first, Rishabh?
Yeah.
Okay.
So that
So
only the interested
first everyone.
participants. Yeah.
Okay, so we'll have a group photograph first, and then whosoever who want to leave the meeting can leave, and then we can start with the interactive session. Okay, so I request everyone to turn on your camera. Yeah, waiting for everyone to join. By the time I'm taking some snapshots. Yeah, so thank you. We have taken the snapshots.
Thank you, Anupama. Thank you.
Yeah, thank you.
Thank you, guys. Priyanka, that was a wonderful talk. Yeah,
Yeah. So,
and
Thank you, everyone.
I hope
yeah. Thank you. So Abhishek sir.
And sorry for delay.
it's all right, Priyanka. Sometimes
No
happens.
issues.
So thank you to participants for having the patience today. Yeah.
Yeah. So Rishabh, we are having
So
interactive session, or you are ending up the meeting?
no, we can have now interactive sessions. Those who want to interact, but please switch off your video feeds so that we can interact without any lag.
Yeah. So Abhishek sir, I request you. Yes. Over to you, sir.